So today's class is about carrier concentration and Fermi level in intrinsic semiconductor. So at the beginning we will find out the carrier concentration in conduction band. So to find out the carrier concentration means how many electrons are there at any temperature in the conduction band which will carry the your electric energy. Okay, so it's the carrier concentration. That's why it's carrier concentration. Now, to find out the number of electrons, what we will do is that we will find out how many states are there which are occupied in the conduction band. If we can find out that, then we will have our number of electrons in the conduction band. So it is an indirect way of finding out the carrier concentration, right? So what we need to do is now to find out the number of states that are occupied. Okay. So to go through this derivation, what we need to do is we have to understand few concepts at the beginning. What are the concepts are that? So we know that suppose this is our the band structure of intrinsic semiconductor. Band structure. Okay. Now suppose this is our valence band. This is our conduction band. So we all know that for a intrinsic semiconductor, Fermi level lies just exactly here. Okay. Now at absolute zero temperature, there will be all the electrons in this valence band, and there will be no electron in the conduction band. But as the temperature rises, the electrons will start filling up this. Okay. Now what we need to find out is that, so another concept is, you see this is the edge of the valence band, so it is EV, we name it. So this is the edge of the conduction band, it is EC. So the electron that has jumped to the conduction band, they cannot have energy below EC. So all of these electrons will have definitely energy above EC. Okay. So the first concept is that the limit of energy of the electron in conduction band is EC to infinity, right? And similarly for the holes in valence band is EV but 0 to EV. Okay, it is 0 to EV. So the thing is, from this diagram you can understand that, so the holes will be definitely be from this 0 to EV, they cannot be here. Okay, now there will be no electron or hole in this energy gap, right? So electrons will be above EC, which will conduct the electric power. There will be electron here, but these electrons in the valence band, they will not conduct. So the electrons which are the holes, they will conduct. Okay, so now the first what we will do, we will find out the number of electrons in the conduction band. So we need to find out how many states are occupied for at a certain temperature, right? That's what we need to do. Okay, now another concept that we need is from our first module. Okay, if you all remember, in our first module we have studied about this density of states. Okay, so density of states, we have this definition. Okay, ZE equal dN by dE. Okay, where suppose this is a potential well, so there are many states, right? So there are suppose 6 states. So 6 is the, so this 6 we can consider this 6 as, suppose there are 6 states, so ZE is equal to 6, right? So how many are occupied? So 1, 2, 3 are occupied, right? So N of E is equal to 3, right? So what will be the relation between NE and this one? with some fraction. How to find out this fraction? Suppose we name this fraction as alpha. So alpha will be equal to NE divided by ZE. Okay, this one will be 3 by 6. This means 1 by 2. Right? This is 1 by 2. Okay, so the relation between ZE and FE will be, so N of E is equal to alpha ZE. Okay, N of E is 3 equal to 1 by 2, and this is 6, right? ZE is 6. So this alpha was our F of E. F of E is our Fermi function, which is dependent on temperature. More temperature increases, more will come to NE. So more will be this number. Okay, so that's the thing. Okay, so now by using this formula, we have derived this expression for ZE, the density of states. Okay, ZE and DE. Okay? This is total number of states. Total number of states. This expression V by twice pi square twice, this will be needed in this derivation. So it is in the first module, and also we need this formula, right? NE DE equal to F of E ZE. Okay. So ZE is the number of available states, NE is number of occupied states, and F of E is Fermi distribution function. So we need these formulas. So another formula is number 3 that we need is N of E is equal to F of E ZE, where N of E number of occupied state. Okay, F of E is Fermi function, and ZE is number of available states. Okay, now another important concept that we need is, let me write here. Okay, so this one will be like 1A concept is belong to 1. Okay? Is that the electron in conduction band will have energy within E minus EC, which means suppose we consider a random energy state here. Okay, so this random energy state, suppose its energy is E, and we count this E from here. Suppose this is E, right? This random state. Okay, there are many states above. This is our random state. So because these electrons are not belong here originally, but they jump from valence band to a conduction band, right? So now their energy possession you cannot count as E from here to here, because they have, you have to meet, because now we say that this is their edge of conduction band. Now for them this is the 0, not here, this is the 0 for all the conduction band electron. So whatever measurement we do, so we will measure them from here. Okay, so the energy that will be belong to this electron will be E minus EC. So E minus EC. So this energy they will possess for the conduction electron, not this whole E. Okay, I think you understand that. And for valence band there is no problem. From 0 to this one we can consider from, because their below is here, their original is here. From here you can count. But for conduction band electron you have to from here, because below this one they cannot exist, they have to come here. So above this one is there, this is their minimum energy. For minimum energy we consider so E minus EC. Okay, this is one concept that you need to know. And another concept you need to know is this one is like your 3A. Okay, this is coming from 3. Oh, sorry, 2A is coming from 2. Now for this 1A, for 1A we consider F of E is the Fermi function, right? But for valence band the Fermi function will be 1 minus f of e. Okay, so but you may ask, why sir 1 minus f of e? It can be directly minus f of e because it is minus of this one, but the thing is it will be minus f of e only when if you want to find out number of electrons left in valence band. If you want to find out number of electrons left in valence band, then your function will be minus f of e because others are left there. But now we have to find out that how many holes have been presented. That's why it is minus 1 minus f of e. Okay.